All right, good morning. So here we are yet again on February 1st, 2017, and for yet another lovely session of MENG 3310 Fluid Mechanics. So this is going to be the 7th lecture in the series, and today we're going to continue on talking about stability, going over another application of Archimedes' principle, or maybe I should say more of a slight derivation or a slight point of note in Archimedes' principle. In the previous lesson, we talked about buoyancy, but we didn't talk about stability of objects in a fluid. So we're going to finish up our talk of Archimedes' principle with a discussion of stability, the difference between center of mass and center of buoyancy, and then we'll move on to introduce the Bernoulli equation. So today we're sort of finishing up our basic understanding or our basic exploration of fluid statics, and we'll be moving on to our first application or our first exploration of fluid statics. So let's talk about stability of shapes. Stability of shapes. So in terms of actual design for a object or a machine or a device or something like that is going to float in water, it is not enough that it simply remains buoyant. For example, consider a large ship. Consider the type of things we put in the water or put in bodies of water. Just some examples we might have. We might have something like a large vessel, like a large ship, and again I'm going to very poorly draw a ship from the front view. Now, it is not enough that this ship remain buoyant. That is not enough. It is not enough that it remains floating above the water, because we actually also care about the orientation of this in the water. See, if this ship is now floating like this, well, even if it's still floating somehow, that's still a problem. And in fact, there are usually enough water-penetrating voids in the top of the ship that if you try to float it this way, water will flow in and it will sink. So it's not good enough. And even if everything was sealed up tight, it would not be good enough for a ship to float like this for obvious reasons. If for no other reason that all of your stairways are upside down now. But I imagine I don't want to be in a ship that's floating like this. What do we refer to this when a ship does this? Remember the word? Yes, we refer to this as capsizing a vessel. Same thing works for certain floating oil platforms. Say like something like a tension leg platform. Well, these things are designed to float upright. They're not designed to float any other way. So you maybe have a structure floating like this, maybe a building up here, maybe you're some sort of flare boom out here, something like that, and then supported by tension cables. That's a very common thing for tension leg platforms and such, although it actually wouldn't have one right there, just one on the sides there. But if this thing is now, if there's a big storm and these cables snap, well, now this thing is the other way and we have a problem. So that's not good, and I'm going to try to draw this upside down. I'm probably going to fail. And it would be obviously something like this. Actually, I guess if this rotated, it would be more like the boom out there, wouldn't it? And this building thing would be right there. Whatever, I'm not an artist. But you get the idea. This would not work so well. The real machines, the real machines, the ships, the vessels, everything that we built to work in the water or work in a fluid, if we are relying on buoyancy to support it, typically we care about its orientation. And so the orientation of objects in a fluid, this is what we're talking about when we say stability. So let's look at something more generic than simply a ship or a vessel. A nice thing about a generic thing is I can draw a potato, and even my poor art skills can render a potato properly. So I'm going to draw a generic mass here. Just a big, lumpy potato mass. Now, as we mentioned last time, the center of buoyancy of an object is going to be at the centroid of the volume of fluid displaced. Meanwhile, the center of mass of the object will be, well, at the center of mass of that particular object. Now, for very simple shapes like a cylinder, these will inevitably line up, but for more complex shapes, like a ship, for instance, this need not actually be the case. So let's look what happens if ideally these two centroids will line up, but let's look at what happens when they don't. Say you have a point here, point X, and maybe the center of mass is right here. So let's look at what happens. Let's look what happens if these forces are not aligned. So again, this is going to be the center of mass of the object, while this point is let's say this is the centroid of fluid displaced. Well, what happens? Well, let's look at these forces. Buoyancy and weight both act purely vertically. The weight of the object is going to act directly downward from the center of mass, and the buoyant force, Fb, is going to act vertically through the centroid of the fluid displaced. Now, these two are going to be equal and opposite if the object is floating. So the magnitude of the weight is going to be equal to the magnitude of the Fb, but these are separated by a distance now. Notice this. We have two equal and opposite forces separated by a distance. This means we have a lever arm. This means we have a couple. We have two forces equal and opposite separated by a couple, and if you remember from good old statics, ENGR 2301, when you have two forces separated by a couple, separated by a distance, you have a couple, you have a rotation. And so you will then get a resulting rotation. This thing will tend to rotate. And so you end up having a torque or a rotation or a moment depending on your perspective. So essentially you have a torque at any point, actually let me say at any rotation, except when Fb lines up with W. And there are two ways to get this. There's two ways to get this alignment. Well, it's fairly obvious. One, center of mass of object above center of mass of displaced fluid. That's very bad handwriting. Center of mass of displaced fluid. Or two, the center of mass of the fluid, or I should just say, center of mass of object is below center of mass of displaced fluid. So two ways to produce the exact same condition. Again, a shape will be stable when, I should not necessarily say a shape will be stable. Let's explore these two conditions independently. So there's two ways that we can end up with no rotation. One is where the center of mass of the object is below that of the fluid. One where they're reversed. And these will actually produce different conditions, as we'll see. So in terms of stability. So let's look at a low center of mass versus a high center of mass. I'll explore each of these independently. So consider a low center of mass first. Let's consider a low center of mass first. Well, we're going to have an object, and I'm going to show it at a certain angle. So let's say we initially had an object. Basically what I'm going to explore is, I'm trying to explore for each of these cases, what happens when we start off with an object like this, with the center of mass below the center of displaced fluid. And in both cases, they're going to start out vertical. But in both cases, I'm going to basically, what I really want to do is I want to disturb them and then see what happens. So in both of, so it starts out like this, and with the buoyant force above the weight, and this is definitely drawn exaggerated. There's no way the buoyant force is going to be that much higher than the thing, but perhaps if I had some really dense thing down in the hole or something. So as I've drawn here, there would be no rotation. But then, let's say I displace. Let's say a wave comes along and displaces the cylinder, so now it's sitting at an angle. Let's see what happens. So now I have this thing at an angle. And the center of mass is still going to be lower than the center of buoyancy. So let me draw that. I have weight here and the buoyant force up here. But look what direction the resulting torque is. The resulting torque is going to be, as I drew it here, is going to be counterclockwise. So this is the resulting torque. Or sorry, it's going to be clockwise. Notice this is a restoring force. The torque tends to restore the object. Tends to restore to neutrally stable. So when there's no rotation, this is what we mean by neutrally stable. It's a neutral rotation. So again, this is what's kind of cool about how, this is why it's very useful to have your center of mass lower than your center of buoyancy. See, what will happen is when this thing becomes displaced, and it inevitably will, anything in a body of water like the ocean, inevitably there's going to be waves coming along, and this thing is going to end up, when a wave comes along and hits it from, say, the right here, it's going to be rotated a bit, and then it's going to experience some rotation. But the nice thing about having the weight below the buoyant force is that rotation will tend to bring it back to equilibrium. So what this thing is going to do is it's going to rotate back, and it's going to gain some velocity as it does, and it's going to go this way, and then the buoyant force and weight couple will be reversed, and it will want to cause it to rotate this way. It'll sort of wobble back and forth like a swinging pendulum for a while, and eventually it'll end up stable. So basically, it will wobble until restored.
There's some ships now that have like some kind of gyroscope on top and stabilizes that.
Yeah, there are some, yes, there are some ships that may actually use gyroscopic stabilization, but even though the difficulty with that is you're dealing with very large forces. Wave forces are very large.
Well, I think it has to do with the wind.
Oh, for wind and such? Okay, that makes sense. Okay, so let's compare the other one. Let's compare the other option, though. High center of mass. You can probably see where this is going, but it's going to be the exact opposite case. Say I have a high center of mass on a vessel or a object or anything. Well, in this case, let's look what happens. Well, here, in this case, when the object ends up displaced by a wave, or really any displacing force, it could be wind, wave, whatever, this time the buoyant force is going to be below the weight, so you end up with the buoyant force acting upward here, and the weight acting downward here. And look what happens. This resulting torque is now going, oh no, oh no. This is bad. This is very, very bad. So look what's happening. When this thing is offset from vertical, it actually gets a greater moment. It gets a greater torque. Offset from vertical causes further rotation from vertical. In other words, this shape is intrinsically unstable. This is intrinsically unstable. So a shape, when we say a shape is stable or an object is stable, what do we mean by that? Well, a stable object or a stable shape, this is one that if displaced, it will return to its original equilibrium position. An object is stable when, if displaced, returns to its initial equilibrium position. Okay, so in other words, when we're designing ships, we want to design them to have the lowest center of mass possible, since that's going to be the most stable. Higher center, if you have a ship with a high center of mass, that can actually cause capsizing. So we want to design ships with a very low center of mass if possible, again, because that's going to make for the most intrinsically stable shape. In fact, if I were to give a very simple analogy for an unstable shape, there is something you can think of from simple dynamics or the mechanics of simple objects, and that is simply a pencil balanced on the point of its tip. If you have a well-crafted pencil, and this thing is constructed, if it's constructed reasonably accurately, and you have so there's the eraser on the end, etc. If you have, that's a really poorly drawn pencil. Anyway, if you have a pencil and you have a sharp tip, or even probably a slightly dull tip, if the tip is cut so it's pretty balanced, if the pencil itself is pretty balanced, if you're in a room with no air currents, and if you are very careful and have very good hand-eye coordination and such, you can actually sometimes balance a pencil on its tip. Have you any y'all ever seen that before? I mean, it can be done. It's difficult, but especially if the tip isn't sharpened especially the tip is kind of flat, you can do this. It takes some practice, but you actually can balance a pencil on its tip. But this is an intrinsically unstable shape. The moment the slightest gust of breeze or the slightest vibration from the table below or whatever comes along and displaces this thing, well, look so a pencil is this pencil is very similar. See, except here what's holding it up is we have a normal force, F normal, balancing the weight. These, as long as this remains vertical, this will be fine. But the moment this thing becomes displaced from vertical, we end up with a torque that is not restorative, but actually will cause further displacement. So when this thing is at an angle then, I cannot draw a pencil to save my life. When this thing is at an angle, the normal force is still acting upward on the pencil from the table, but now the weight still acting from its center of mass is offset. This is causing a rotation or torque, which causes even more displacement from the vertical, which causes the torque to grow even larger, and before you know it, the pencil is sitting on the table. So a pencil resting on its tip is an intrinsically unstable shape. So kind of interesting. And in fact, because a pencil actually has to be supported by a normal force, it doesn't actually matter whether you balance it on its eraser or on its tip. If you try to support a pencil vertically, that is still going to be an unstable shape. You can't really have this kind of stability like this in an object unless it's being supported by some body force that is generated within the volume of the object. Now, we do sometimes actually design objects with the center of mass. There are cases where you design objects, floating objects, large floating objects, with their center of mass highly above their center of buoyancy. Anyone aware of some cases like that? I'm aware of a few. Sometimes you see this in floating oil platforms. So you can't help but have, in a floating oil platform, you almost can't help but have the center of mass be higher than the center of buoyancy. It's almost unavoidable. Simply because the whole point of the floating platform is to support a bunch of equipment high above the waterline. That's the entire reason for the existence of the platform in the first place. So why did I draw that like that? That's not right. It should just be a single line. So say you have a surface like this out in the Gulf or something. And you might have something like, say, a tension leg platform. Like I kind of drew a bit earlier. And they'll have a hull. The tension leg platform has a hull with a series of compartments in it. And the way this thing is designed to work is that there are, so there's the platform, there's the actual decked platform above this that everything that carries all the equipment, buildings on top, access buildings, all the oil drilling equipment, access platforms, booms, supporting pipes, all that kind of stuff. Lots and lots of big, heavy equipment. So, but it all needs to be held very high above the waterline. A lot of your pumps and equipment don't like being submerged in salt water, so the entire point of this platform is to keep all this stuff, all these electronics, all these pumps, all of this big, expensive mechanical equipment high above the waterline, because if it's submerged in salt water, it tends to ruin it, and you have a bad day. So the way this thing works, though, is, this thing is supported buoyantly by the tanks, by the empty tanks and hollow spaces inside the sort of bottom U shape of the structure. And actually, if you were to look at this from above, it's not really a U shape. It's more like a hollow square. So if you were looking at it from plan view, if you were to look at just the hull from the plan view, it kind of looks something like this. It's sort of like a square shape, hollow in the middle. It needs to be hollow in the middle so you can have your drilling pipes and things going down through here. But anyway, the point of this is, again, to hold this stuff high above the waterline. So your buoyancy is supported down here, but your weight is inevitably going to be up here. So then the question is, why don't these things just tip over? So you have your buoyant force being generated somewhere down. Oops, I've ruined everything forever. I have truly ruined everything forever. Well, I have destroyed my oil platform. So the center of the buoyant force might actually be somewhere like this. The buoyant force might be somewhere like this, and the center of mass might be somewhere up here, with the weight coming here. Well, the way this works is, it's actually, we do need some sort of restorative force. And where that comes from in, say, a tension leg platform is, well, exactly as it describes, the tension legs. You may not be aware of how these things operate, and that's fine. It's kind of a niche thing not many people know about. But the basic idea of a tension leg platform is that you will, this thing will let me sort of draw this a bit exaggerated. You float this thing out there. I'll draw only the hull for simplicity's sake right now. Sometimes it's actually sent out with just the hull, and then the top sides are loaded on top later. Or sometimes they're joined together and then sent out, just depending what you're doing. What they tend to do is they float this thing out there with the hull just barely above the waterline. They float it out there like this, with the tanks mostly full of water. Then they float this thing out there, and they attach the cables, the legs, the tendons they're called. And these tendons are not little strings. These are like big giant pipes, essentially themselves. They're long lengths of welded pipe. And so they float the hull out there, attach the tendons to it, and then they pump the water out, a lot of the water, not all of the water, but a lot of the water out of the hull. And so that means the hull then wants to, that means the hull then wants to float higher in the water. So I'm going to try to draw this a little bit higher. It's now floating higher in the water, and because the tendons are actually anchored to the seafloor, this generates an immense tensile force in the cables, in the tendons, simply via flotation. So you float this thing out there, with it low in the water line, because the tanks are mostly full, you attach the tendons to them, then you pump the water out, and now the cables go extremely taut, and they are going to generate an immense tensile force at the legs of the hull, or of the structure here. So you have this immense tension force that will then be holding the platform in place. And so then what's going to happen is, and these tendons can be quite long. They can be hundreds and hundreds of feet long, sometimes up to 2,000 feet of water. And there are other tension-like platforms I think are good to about 1,000, 2,000 feet of water. Beyond that, you need to use other platform designs, or even do just subsea drilling. But anyway, so you get the tendons to generate this enormous tensile force. And then suddenly, now we actually have a way of making this previously unstable structure now stable. So again, the tendons are generating there's the hull. And look I'm going to show what happens when this thing becomes displaced. So the tendons are normally vertical, and I'm definitely going to exaggerate the deformation. But initially they're vertical, and they're still generating a force, but it's a purely vertical force. The buoyancy is being resisted by tension. So you have tension here, tension, and buoyancy, FB here, and then also weight. Well, maybe you have weight more up here, and then buoyancy here. Well, when this thing becomes displaced, well, suddenly the tensions are now acting like this. Tension like this, weight like this. Oh, that should be, I really screwed that up, didn't I? That should say weight here, and actually maybe put it more up here. Sorry about that. Weight here, buoyancy here. Weight does not point upward, we know this. Weight here, and buoyancy here. That makes me happy. Like this. And so these are now, if this becomes displaced horizontally, well, this is going to generate a restorative force horizontally here. So if I displace this thing horizontally, then these will generate a restorative horizontal force to bring it back into alignment. Or look what happens if I rotate this at an angle. Let's see what happens if I rotate this at an angle. So now I'm going to have my plot. This is definitely exaggerated. They never actually deform this much or displace this much. You would have a problem. But if you did that, well, this tension force here, initially these two tension forces are the same, but this tension force would be, you would basically have slack in this cable, so this tension force would be much decreased, and this tension force would be much greater. And now the buoyant force would be offset now. So the buoyant force would be like this, and the weight would be like this. So this would be generating a torque this way, right? But this one would be generating a torque this way. So the tensions, the difference in tension, will actually be able to generate a stronger torque, or a torque that is stronger than the offset of the center of mass, center of buoyancy system. So this is just sort of a hack, you might say, a hack to get around the method, to get around the problem that a floating hull, at least for an oil platform type design, is often intrinsically unstable. Now, yes, you could counter this by just putting a lot of ballast in this, you could put a lot of ballast material, dense ballast material at the base of your tank. But for these types of structures, because again, the entire point of this thing is to have a lot of mass very high above the water line, that's very difficult to do. So that tends not to happen. But this is just one way around the problem. You have these huge, immense tension tendons that will counteract both lateral drift and rotation, and that turns a system that would otherwise be unstable into something that can actually last for decades in service. But in terms of traditional ship design, though, how do you usually handle this? Well, in traditional ship design, even ones that have things high above the waterline, have a lot of mass above the waterline, you tend to handle this via ballast. The idea of ballast. So if the ship would otherwise have, well, okay, let's talk about this. What is the disadvantage of simply having a bunch of mass below the waterline? Know what a disadvantage of that is? Well, one big disadvantage of that is, look what happens if I design my ship to do that. Well, this would be an example of a ship that has a lot of mass and buoyancy below the waterline. It would be something like this. It would be just a big, it'd be like a barge, something like a barge. But the downside of this is it's not going to be very stable in the water. It's going to generate a lot of drag. So for something like a river barge, it's not really a problem. Drag isn't such a big consideration. You're just sort of going down the stream, going along with the flow of the current. It's not a big deal. But something like a large ocean-going vessel that is more vulnerable to waves, that's going to see higher waves, that needs to go a long distance under its own power, drag becomes a dominating factor. So you tend to see this type of thing with a proper keel and a proper sort of a tapering hull design, the kind of ship design that people have been designing for eons. But what people usually do to make this stable is to use a kind of thing use the idea of ballast, and ballast can be any number of things. The whole idea of ballast is to put a lot of heavy, dense material at the bottom of your vessel. So right at the bottom of your vessel, you put heavy material. So what can that be? Well, that could be, in a simple case, usually you'll have like water tanks and things like that. If you still need more ballast, if water tanks aren't enough to do it, you might use something like, things like even concrete, or steel or concrete or something like that. But in more historic examples, if we were to go back to the days of, if you were to look at, say, the days of tall sailing ships, they had a real problem with ballast and stability, was because by their very nature, they needed to have a great deal of mass high above the waterline, because that's how they were going to propel themselves. In the days of wooden sailing ships, the only way that the ship would propel itself would be to have large sails above the waterline. So that means you need a large amount of mass with a large moment arm high above the waterline. And of course, this tends to cause rotation. So they would tend to have quite a bit of ballast in them. If they were carrying, they would put like their heaviest cargo at the bottom. If they were carrying cargo, that's where they would store their water barrels. That's where they would store any kind of, these were Spanish galleons hauling gold, they would put the gold way at the bottom of the ship. They wouldn't put the gold way up at the top. They'd put it at the bottom of the ship because gold is really heavy. And in certain cases, they would even, if they found their ship was unstable, they would actually literally pack rocks. They would go out to a nearby shore, they would find the heaviest rocks they could find, and some poor sailor had to get out and, go and haul rocks in from the shore on a little boat, and they'd lift them up and put them in the bottom. And in fact, even today, people who go and explore for historic shipwrecks, one of the things they look for is piles of rocks on the bottom of the ocean, because it's very you don't tend to actually see, if you're trying to find a wreck in tropical waters from 400 or 500 years ago, well, wood rots, and especially after 400 years, there's basically no wood left. And so there may be some interesting bits of metal and things that you can find in the bottom, but if you want to search a large area, you're going to need to search via some sort of sonar method, some sort of radar imagery method. You can't just send down divers and manually search the entire thing. You need to have some sort of vessel on the surface scanning a wide area looking for anomalies on the bottom. And one anomaly that marine archaeologists actually look for, if they're looking for this type of shipwreck, is to actually look for big piles of rock on the bottom of the ocean, because when this type of ship got sunk in a storm and sank to the bottom, well, it would sit there. Eventually all the wood and the sails and the hull would rot away, just leaving the pile of rocks on the bottom. And so the pile of rocks can still sit there. Rocks are rocks. They'll happily sit there for hundreds of years. And if it's in deep enough water, the currents and the storms and such won't disturb those rocks. And it's kind of it actually is, you know, there are rocks on the bottom of the ocean, but it is kind of actually fairly unnatural to see a big pile of rocks just conveniently placed in one big mound on the seafloor. That's not a natural formation. So that can be a clue to actually, that's one of the things they'll look for when they're looking for possible sites to actually send divers down to. But there you go. So that is the idea of stability going along with buoyancy. All right, any questions on that? Okay, I think it's fairly straightforward, but I just wanted to discuss buoyancy and its ideas, its principles there. All right, let's see how we're doing time-wise. You know what? I think we can. Yeah, we can introduce buoyancy. Or sorry, we can introduce briefly the energy method and Bernoulli's equation. So we're done with Archimedes and we're moving on to Bernoulli. So I have a few objectives for this portion of lecture and also going into Friday, going into lesson 8, which to describe the assumptions related to an ideal fluid, apply Bernoulli equation based on conservation of energy flow, and apply the Bernoulli equation to different systems. So a lot of what we're going to do in this class is based upon the idea of conservation of energy. So let's recall from physics. If you recall from physics, even elementary, high school physics, you may remember energy methods. And I love energy methods in physics class. They were great. I love energy methods. And the real great thing about energy methods is that they're path independent. See, with energy methods, it doesn't matter what kind of path an object takes to go from point A to point B. It doesn't matter. It doesn't matter if it goes down a ramp like this. It doesn't matter if it falls down. It doesn't matter if it goes kind of through a crazy loop-de-loop roller coaster pattern. It doesn't matter. As long as energy is not being lost from the system, all that matters is the beginning state and the final state. So, for example, here at t equals 0, in this case, PE, potential energy, is equal to mgh. This is just describing a block or a mass going through a change in height, and kinetic energy would be equal to 0. Then at the bottom of the path of the object here, kinetic energy would be 1/2 mv squared, and PE, potential energy, would be equal to 0. So again, this is the basic idea. At t equals t final, kinetic energy equals 1/2 mv squared, and potential energy is 0. So in other words, in any system, and I'm talking very generically here, if any system, if our system, I should say, has no external forces acting on it, then KE, basically the energy final equals the energy initial. So KE plus PE 1 will be equal to KE plus PE 2. i.e., we might say this as i.e. change in energy is work done. If there's any change in energy, it is because there is being work done by an external force, by external forces. Is work done by external forces. So if there's any change in energy, it's going to be caused by work done by external forces. And in our case, that can be a few things. So this is really going to be the basis for Bernoulli. And we will see, I'm going to work through the derivation of it later, or see, I'll work through its first applications on Friday, but I will just say Bernoulli is applicable to systems with no exchange of energy, with no overall change in energy. Later in the semester, we can use further equations, use modifications of Bernoulli, I should say, of Bernoulli to deal with changes in energy, to deal with energy being lost or gained from the system. Being lost or gained or given to the system. Lost by, maybe. Lost by or given to the system. And the things that tend to cause this kind of energy change are system, really, Tanya? Okay, system are things like, pipe loss, things like friction, things like pumps and turbines. And we'll discuss these as the semester goes along. But right now, in our first derivation of Bernoulli, we're going to be working with ideal fluids that have no viscosity, that will not lose energy. We're going to start with the very simplest applications of this very simplest cases, and then sort of the most ideal physics form of Bernoulli, or the energy equation. And then as the semester goes along, we'll start looking at more realistic systems. We'll actually look at systems that do have pumps or turbines, pipe losses, etc., and we'll actually learn how to calculate some of these things as the semester goes along. All right, so that will do it for today. If you have any questions, please see me during my office hours. We'll continue with the actual first showing of Bernoulli on Friday. That'll do it for today, and as always, thank you.